another class of functional materials that are quite widely used and that have a lot of potential for many applications. Okay, so we'll look at the introduction. Just like magnetic materials, what are different type of piezoelectric materials, how the piezoelectricity originates, and what are the applications, and so on and so forth. Okay, so but there's also another class of materials, photovoltaic materials, right? Well, which convert light to electricity. So the light domain and the electric domain are coupled. Okay, in piezoelectric materials, it's the mechanical and the electric domains are combined. In photovoltaic, it's the light and the electric domains are combined, right? So in photovoltaic, you put a light on the material and it gives you voltage, and that's what you make use of in photovoltaic cells. Um, and the converse of those are the opposite effect of photovoltaic devices is LEDs that take the electricity and give the light, right? So it's a similar phenomena, but they're very different in terms of engineering the materials. Okay, so piezoelectric and photovoltaic, there is a possibility to combine them to harvest energy. So we'll look at the hybrid piezoelectric and photovoltaic materials as well. Okay, so how many of you have heard piezoelectric materials before? Yeah, and we already talked about the most commonly used piezoelectric material, which is quartz, right? Quartz is a piezoelectric material, and you apply a voltage on it, it changes its dimension, or you press it, it produces a voltage. Okay, so quartz is one such piezoelectric material. Quartz is nothing but silicon oxide, right, or dioxide, SiO2. So, but it's in a certain crystal form. Then there are polymer piezoelectric materials. Then there are other ceramics that are piezoelectric. So we'll take a look at them. Okay. So the direct piezoelectric effect is when you apply a electric polarization or a voltage, and sorry, when you apply a stress, you get a change in electric field or change in voltage. That is the direct piezoelectric effect. Okay, so you apply a stress and you get a voltage. That is direct piezoelectrical effect. And the converse piezoelectric effect is apply electric field or apply voltage, and you get change in dimension or change in strain or stress. And that is converse piezoelectric effect. And so not all piezoelectric materials are ferroelectric materials. Again, ferroelectric materials are similar, like the classification is similar to ferromagnetic materials. Like if you remember how ferromagnetic materials have hysteresis, just like that, ferroelectric materials also have hysteresis. But instead of magnetization and the field, here you have applied electric field, and instead of magnetization, you have what is called as polarization. So if you apply electric field in volts per meter, and this is polarization. So this is virgin. Okay. You have the same hysteresis graph for ferroelectric materials. Okay, and then there are dielectric materials which are similar to diamagnetic materials. Okay, so not all piezoelectric materials are ferroelectric materials, and some subclass of piezoelectric materials are pyroelectric materials as well. So can anybody think of what that is? Pyroelectricity or pyroelectric effect? Yeah, pyro means fire, temperature. Yeah, so change in temperature will give you change in electric field, or when you apply temperature change, it will give you voltage, or when you change the voltage, you get a temperature difference. Do you know there are famous devices using pyroelectric? So thermocouples is, yeah, using pyroelectric. Something called Seebeck effect as well. So Peltier cells, or you can take Peltier cells and use them to heat or cool by applying um, a voltage. So these are um, another class of piezoelectric materials. And then ferroelectric materials are all these here. Piezoelectric material, these are all piezoelectric materials, but quartz is a piezoelectric material, but it's not a pyroelectric material, or it's not a ferroelectric material because it doesn't show hysteresis. Okay, so the other piezoelectric materials that are ferroelectric and pyroelectric are PZT. So PZT is lead zirconate titanate. Okay, so zirconium is an element, transition element. Titanium is also another element. Lead is a heavy metal. So when you combine these, it becomes a ceramic material, and that ceramic material is um, piezoelectric or and ferroelectric as well, and pyroelectric as well. And then we have PM and PT. This is lead manganese. I think this last one is titanate. I'm not sure what is P. And then we have PVDF is a polymer, polyvinylidene fluoride. Okay, so these three materials are very common. Then there is another version of PVDF called PVDF TRFE. So it's a copolymer that has better piezoelectric coefficient, meaning its polarization is much higher. So again, because these two are very different class of materials, usually magnetic researchers and piezoelectric researchers do not talk to each other that much because they have very different applications, and they are also different class of materials. Magnetic materials are metals, piezoelectric materials are ceramics. So people who work with piezoelectric materials have completely different skill, have completely different perspective of the materials, because when they think of their functional materials, they think of ceramic, which is inert, high temperature, not ductile or malleable, it's very brittle. Whereas magnetic people, when they think of their material, they think of malleable, metal, iron, cobalt, and rare earth materials. So yeah, so these are very different areas of research. So, but there is now a hybrid class of materials called magnetoelectric materials. So what that means is you change magnetic field to change polarization. But magnetism and electricity are coupled anyway. It's very common to see, for example, a conductor gives you a magnetic field. So it's wherever there is charge in motion, there is always a magnetic field. However, it's very difficult to use the magnetic field and change the polarization. Okay, so you can get with magnetic field, induced electric field, but and again, these materials are also non-conductive materials. Their conductivity is very weak or very small. So the resistance of these material or dielectric constant of these materials is quite high. Okay, so so the notion of piezoelectric materials was first described by Charles Coulomb himself. Coulomb is the person who described charge. So that's way back in 1817 because it existed in quartz and other natural materials. And then Pierre and Jacques Curie did a lot of work on polarization in 1880s, but name piezoelectric material is given by Hankel. So then they discovered piezoelectricity in barium titanate. Barium titanate has polarization or has piezoelectric constant, but it's not as good as PZT or PMNPT. And then when lead zirconate titanate was discovered, this is a man-made material. This did not occur in nature. So this happened in 1952. That's why it took so long after we knew about piezoelectricity to discover in lead zirconate titanate. Then the applications ballooned because this has high piezoelectric constant, D33 constant, so you can use PZT in many applications. Okay, and then came in 1969 piezoelectric effect in polymers, and now PZT is a ceramic, very hard to work with. The polymers are easy to work with, they're flexible. So this opened up other type of applications. Okay, so this is a rough introduction to piezoelectric effect and piezoelectric materials. Okay, so here are so many man-made piezoelectric materials. So barium titanate, I talked about, lead titanate, lead zirconate, and lead zirconate titanate. Okay, so these do not have so high piezoelectric effect, but this shows very high piezoelectric effect. So this is very popular. And then there are other ones which do not show as high D33 or constant or piezoelectric coefficient as PZT, but nevertheless they exist. And then we have PVDF. So there is polyvinyl fluoride and then polyvinylidene fluoride, PVDF. So this the difference is just the molecular structure in the chain. And then PP, polypropylene, is another very cheap polymer. Probably polypropylene is in many, even straws. I think drinking straws are made of polypropylene, or many toys are made of polypropylene. And PVF especially, is lots of pipes are made of PVF. So these are very common polymers, but they are not inherently piezoelectric. So if you go and hit a pipe and connect voltmeter, it won't show you because you have to pole it in order to make it piezoelectric. Okay, so PVDF is a piezoelectric polymer that shows very high piezoelectric coefficient. And then there are other polymers, even cellular. I don't know what this is, but this is some cellular based material. Even they show piezoelectric effect. And apparently our bone also is piezoelectric. Don't try it. Don't try to whack it and measure the voltage. But yeah, apparently bone is also piezoelectric. So you can actually, if you know how to just like we know how to make magnetic materials. So you have to have unpaired spins, right? Because magnetism originates from unpaired spins. You just make sure that those unpaired spins again don't combine with another unpaired spin. You make your crystal such that you retain one unpaired spin, which gives rise to magnetism, right? Just like that, if you know how to, okay? So, so yeah, if you have a distribution like this, and when you apply a force, the the charge symmetry changes, and there will be net polarization. Or if you expand the material, you also create asymmetric charge distribution, and then you get net polarization. That's what that figure explains. Okay, so that is the origin of piezoelectricity. So now, how do you quantify it? Piezoelectricity is quantified by a constant called D31 or D33 constant. You can also quantify it by G33 or G31 constant. Um, Here are the comparison of different piezoelectric materials and their different properties. Density, you can see PVDF is a polymer, so it has a low density. PZT is a ceramic, so that's why it has a high density. And then you have barium titanate. Relative permittivity, it's not permeability. So if you take the slope here, we used to get relative permeability for magnetic materials, right? But if you take the slope here for uh, ferroelectric hysteresis graph, that is polarization by E field, change in E field or change in polarization, the slope of that curve gives relative permittivity. Okay, so that is 12 for PVDF and 1200 for PZT. So that means these are much more sensitive than PVDF. Okay, so constant is nothing but amount of charge produced when you apply a unit of force. Okay, so here it is in terms of 10 to the power minus 12. So 10 to the power minus 12 is pico, right? 10 to the power minus 9 is nano, 10 to the power minus 12 is pico, and 10 to the power minus 15 is femto, right? So it's a pico coulomb per Newton. So if you, 1 Newton is what? So suppose if you drop a 1 kg ball, you get 10 newtons, right? If you drop 100 grams ball, you get 1 Newton, okay? So 100 grams ball, if you drop it on a PVDF, you get 23 picocoulombs, which is a very small charge. But nonetheless, it's a charge that will accumulate if you have uh, again, it's also it should be volume based. So yeah, the charge is for specific area of the material. If you have larger area, you get larger charge. So PZT has higher D31 constant, so that means it produces higher charge. So you can see PZT has much higher of everything, although relative permittivity is slightly smaller than barium titanate, but the D33 constant is much higher. Um, so uh, whereas G31 constant, you want to, this is medium, this is how much millivoltage you generate per Newton. This is charge, this is millivolt. No, this is voltmeter, this is millivoltmeter, okay? So We will ignore this, but let's just use D31 constant as a quantity that, or as a parameter that quantifies piezoelectric effect. Okay, so D33 or D31 constant is what we normally see to see whether a piezoelectric material is strong, it has strong piezoelectricity or not. Okay, and here is this is another, I think this is D33 constant. This is quartz is really low. You see 2.3 compared to lead zirconate titanate. This is probably, this is I think D3 constant rather than D31 constant because it's 120. So D33 and D31 is just in a where you measure, in which direction you measure. So D33 is normally what is commonly referred, and here is PZT phase diagram. So if you remember, we'll talk about phase diagram in later class today of other materials. Whenever you want to make any material, the first thing, of course, you make composition, right composition, and then once you have the composition, that's not enough, because for the same chemical formula, you can have multiple phases or multiple crystal structures, right? So you need to look at the phase diagram. So if you are making any new material, you can't talk about it without its phase diagram. Okay, so this is a ternary phase diagram. So where lead zirconate and lead titanate are on the each side, and as you start to add titanium, so here in the middle you get a mixture of titanium and zirconium, so lead zirconate titanate. I think the one that is commonly used is, and this is the Curie temperature. So we want to have as high Curie temperature as possible. So somewhere here, maybe where you want to make the lead zirconate titanate. Okay, so this is the phase diagram of lead zirconate titanate. Now coming to applications, there are, so okay, let me ask you, so what are the applications you can think of for apart from watch? We saw the watch. So you apply, basically you apply voltage and you get change in dimension. So how can you make use of this property? Good. Name, guess something. You have some. What do you, I mean, if a material changes its dimension or its shape when you apply voltage, what can you, where can you use it? Sorry? Okay. Yeah, so breaks, but yeah, that could be one application. And somebody was saying solenoid. A solenoid to me is winding of copper wire that generates magnetic field. But there are solenoid coils which are slightly different, but that they use magnetic field, not piezoelectric. Those are, what are they? What are solenoid coils? Yeah, solenoid coils change. Yeah, it's a switch, right? So what is it? What makes the switch happen? It's actuation, right? It's an actuator, right? So whenever some material changes its dimension, that means it's actuating. You can use it as an actuator, right? Actuators can be used as switches or for any motion, basically, right? Um, so what about the inverse effect? So that means if there is actuation, or if there is pressure on this material, it generates voltage. How can you make use of the inverse effect? So the forward effect is it's very simple. So it can be used as an actuation. So you just apply voltage and it actuates, right? There are so many places where you can use it. Actuation to open windows or to basically, in doorbell also, you press, that is a solenoid coil. It basically goes and hits a round metallic structure. That's actuation, right? You can use these also as actuators. So what about the other side, converse effect? If there is pressure or actuation, it generates voltage. How can you make use of that? So you're generating voltage. You can use them as sensors, right? You can use them as pressure sensors or actuating any movement sensors, right? That's one application. What else? Sorry? When, so that means you can generate voltage when there is motion, right? Okay, so that's really interesting. If that is the case, how come we don't see these materials generating voltage or generating electricity for us? Yeah, yeah. So, okay, that's the use of pizza. We'll talk about that. That's one application. So, I wish that was successful, but that's, every application comes with some caveat. So, these are the applications, right? So, you can generate electricity, or you can use it as a sensor to sense pressure or actuation, or you can use it as an actuator itself, right? How many of you have used atomic force microscope, PhD student guys? Atomic force microscope, no? So atomic force microscope basically images surface of any material and measures the roughness to an atomic level. So the roughness could be 0.1 nanometer or 1 nanometer. The way it does it is a small cantilever traverses on the surface, and there is a laser that is, so this cantilever is at a resonant frequency, and the laser is uh, it's shining on the cantilever, and the detector is detecting it. But whenever it oscillates, it knows the oscillating frequency. But if the oscillation changes because of the bumps, that small change in the current of the photodiode can measure how big is this bump. So that's how you correlate. But the way you oscillate this cantilever is by piezoelectric. And these are very popular as actuators because the current or voltage versus displacement D is maybe, I don't know if it's zero, but it's linear. Okay, so that's very important, the displacement. Although the polarization is not, but the displacement is very linear, and that's why these are quite widely used. So now we're talking about applications. You may not know it. They are used in so many places because these materials were known so long ago. So, for example, ultrasound, when you go for a baby health checkup, the sonography, the the crystal, the actuator there is nothing but a piezoelectric actuator that generates these ultrasound waves, because you send a electric signal with certain frequency and it vibrates at that frequency, and that is your ultrasound. Okay, and similarly, any sonicator, right? Ultrasound you need to generate, you need piezoelectric crystal. You can also use magnetoelastic materials. The terphenol D, US Navy invented that material. That was actually used in US Navy sonography. I mean, to map the sea floor and also to detect enemy's ship. And these are also used in medical for sonography, okay, for ultrasound imaging. And ultrasound imaging, probably you might have heard, not just for imaging also heart nowadays. What is it called? Sonocardiogram, no? Echocardiogram. Not sonocardiogram. Echocardiogram also uses a piezoelectric crystal. And it's so accurate that you can actually measure the blood flow, how much amount of blood goes into the heart, how much comes out. And you can also measure how many fingers the baby has, whether the baby has any defect. The gender of the baby can also be determined. So it's that accurate, okay? So that's because you can control its displacement very accurately. So that's you supply current and then you measure or you get a displacement. And in automotive also, lots of actuators actually use piezoelectric actuators. So as in atomic force microscope. So these are all supply current and get a displacement, right? This is kind of actuation. Computer, I'm not sure. Probably some. Can anyone think where computer uses? I don't know. So we can check that later. In military, of course, ultrasound is used for detecting enemy ships. And now, the other way, instead of supplying a voltage and getting a displacement, can you now use some mechanical actuation or mechanical pressure to generate voltage? That is energy harvesting, okay? This is also some consumer products where you can have it in your shoe and you can get lights on the shoe, or you can use supercapacitors to even charge a small electric component, okay? And this is the one where you are talking about the Japanese floor, but this is also done in London. A dance club made the floor with piezoelectric polymer, and they were powering all their LEDs in that dance floor with the piezoelectric polymer. So that's how you can generate voltage, okay? So you can produce electricity out of human motion or any other motion. So between 2010 and 2015 or 2000 even up to 20, this field of generating electricity with piezoelectric material was very popular. And Yeah, in 2011, I also worked on PVDF materials. So people were even thinking of we can make trees that have PVDF leaves, and when there is wind, you can generate electricity, and you can generate electricity while walking, and so on and so forth. Okay.
Imagine generating energy with the push of a button. An Israeli company has come up with a way for some of the biggest energy consumers on the planet, cars, trucks, and ordinary people, to generate energy by simply doing what comes naturally, moving across a surface. By embedding generators into roadways and sidewalks, Innowatek has found a way to turn pressure into energy.
We're taking that energy that is going to waste and transform back in useful energy. This is the main motivation of using piezoelectric embedded under the asphalt.
Piezoelectric elements, commonplace in everything from doorbells to speakers, are capable of generating an electrical signal based on pressure. So, for every car tire that passes over the element, a current is generated. And the concept isn't limited to roadways.
Pedestrian can provide the pressure for the piezoelectric generators to produce also energy. The problem is that their pressure is less compared to vehicles, but they can compensate it by big numbers of pedestrians.
Innowatt Tech believes it can generate energy up to 50% cheaper than solar generated fuel without the cost of the associated infrastructure. While no concrete plans are in place to start implementing the technology, Innowatt Tech says it is in negotiations to begin embedding generators in Israeli roads. Tim McGuire, The Associated Press.
Okay. So why, in that case, we don't see power generation using PVDF or piezoelectric materials? Why did it fail, or why is it not popular? Why people stopped it? Now, if you go on Google and look for piezoelectric energy harvesting, you get like home-based projects, nothing like that. And when I was doing it, everybody was thinking big. Like every government was thinking, oh, we will lay it in our roads. So why do you think it failed? Sorry? So cost, right? So, well, in that video, he said he's 50% cheaper than photovoltaic back then. But the photovoltaic price came down so rapidly. Now, people, you don't have to put it or dig up the road or do anything. Just put it on the house, you get electricity. So the price per watt of piezoelectric uh, electricity is way high compared to the current photovoltaic or coal power or hydroelectric power. So it could not match up. So big projects gone. No one wants to. It's just a white elephant, just for show. So that's how it failed. But for other applications as actuators, it's great. For transducers, for ultrasound, or even sensing, amazing. Okay, so those are the applications. Now let's come to the PVDF polymer. So here is the naturally occurring PVDF polymer. Okay, you see, if you look at the charges here, it's well balanced. The charges here is well distributed. If you look at the electrons and protons distribution here, negative and positive charge, you will get uniform distribution and net distribution is 0. But that is called alpha phase of PVDF. But if you look at beta phase of PVDF, the two fluoride atoms come on top, and the carbon atom, carbon or polyvinyl, these are fluoride atom, and this is the carbon atom comes at the bottom. So you get, the carbon and hydrogen ethyl molecule is black and carbon is red. Okay, so this has some charge. It's fairly neutral, but if you see, there is a charge separation there. The charge distribution is not symmetric in this phase, and that's why this phase doesn't exist naturally. This is the natural phase. If you take PVDF pellets or grains and melt it, and this is what you get. Okay, and to get this is piezoelectric because charges are separated. You get a polarization, or if you whack it, you get even more higher polarization, right? So that is beta phase and alpha phase. And if we want to make a piezoelectric PVDF, we want to convert all alpha phase into beta phase, right? And the process of making that is nothing called poling. Okay, you pole a material to make it piezoelectric. My slides are a little random. I should have shown you polling, but before that, I'm showing an application. But that's one. So when I embarked on this project immediately after my PhD, and so we wanted to make PVDF, piezoelectric PVDF fibers that can be knitted or woven into garments. And so that means you can wear a t-shirt which generates electricity and charges your phone, or you can put a tent, flag, sail, whatnot. So very ambitious. This project was funded by UK government, and I was the primary researcher. I was the postdoc, and my professor Elias Fars, he got the funding. So we were working on this project, and after my PhD, it took 1 year, and during that time, I did not want to have zero publication because it took time to make fiber, and then we had to patent it, and then patenting takes time. So until then, for about 2 years, you may not have any publications. I thought, okay, let me do a simple experiment, and a new PhD student joined, Derman from Turkey. So along with her, we set up simple comparative experiments wherein we took a PVDF film and put it in a wind tunnel and recorded the voltage and changed the wind speed and just quantified basically for different speeds. And then we started simulating rain as well by there is a syringe here, water droplets falling on PVDF. And when water drops, the PVDF film oscillates, and that generates electricity. And we said if the water droplet is thicker, thinner, we did all this quantification, and then we published that in Smart Materials and Structures. And this is one of the highest cited paper of mine. It's just, I was not proud of it at all. It's just taking some commercial PVDF film and putting some water, putting it in a wind tunnel, and just quantifying. And I told Derman, the PhD student, we'll just do some comparative study write-up and submit it. And we submitted, and they accepted, and it got so many citations because we said, I think the title was Investigation of Energy Harvesting from Renewable Resources with PVDF and PZT. We compared it with PZT film as well. So, and it was also selected as the title of the cover page of the journal. So that was just without doing anything, it got so many citations. But anyway, so my goal was to make PVDF fibers that are piezoelectric. They did not exist before. When I started in this project, the fibers that existed were ceramic, PZT fibers, like that. And they were like noodles, and you just bend a little, not cooked noodles, but the spaghetti, if you bend a little, it'll break. Okay? So we wanted to make polymer fiber that was piezoelectric so that we can knit or weave into a garment to generate electricity. So we eventually did that. Um, but before that, there are from the same lab, there were other researchers who did composite materials with PZT, and top you have polymer with electrode, so that PZT doesn't break quickly. You embed it, sandwich it in a polymer, so you can bend a little. But if you bend too much, it will still break. So they were making these composite structures. So we made this PVDF, piezoelectric polymer. So we took polymer granules, extruded them into fibers. We cooled it a little. And then while cooling, we applied a high voltage of 1 megavolts per meter, which is about 10,000 per centimeter. Okay, 10,000 kilovolts per centimeter. And then while you apply that voltage, and when it is hot, you stretch it by 4:1 extension ratio, keeping it at 80 degrees. This process will give you the beta phase. You convert all the alpha phase. Here, when you extrude, here the fiber is in alpha phase, and here it becomes beta phase. You get a piezoelectric fiber. Okay, so this is here is the hopper that melts, and the fiber comes here. I don't know if you can see a fiber. There is one fiber here, and so is the die. We cool it, melts here, and the fiber is drawn. It's cooled a little, and these rolls pull it so that the fiber goes around, and this is again, it heats up. This roll, this final one, this one, it has a heater that heats up to 80 degrees centigrade. And then here we apply a voltage of 13,000 volts. I thought it was 10,000, but 13,000 volts on this fiber. And these two rolls are maintained at, this is 4 times faster than this. So the speed of this roll is 4 times faster than this. So that means it's stretching by 4 times, or the stretch ratio is four times the whatever you get here. So the speed is by 4 times, so you get 4 times stretching, and this whole process is called polling. And that's how you make piezoelectric polymer. Okay, and then the fiber that comes out, it's in this one, it's somewhat thick. It's about 1 millimeter thick, but you can change the setup. Again, this was an old extruder that was used for other polymers. We got another new extruder that was able to make 0.1 millimeter. Now we characterized those polymers, and we looked at alpha and beta phase in an FTIR. So do you guys use FTIR here for characterizing materials? So FTIR is similar to XRD. This is another equipment which will give you different peaks, and those are signatures of different phases. It's popularly used for polymers. And here, this is XRD. So in XRD, if we uh, take the measurement on our fibers, and the top fiber is the poled fiber and the bottom fiber is unpoled fiber. So that means this has a lot of uh, alpha phase, and this has a lot of beta phase, and beta phase is this peak. Okay, this is alpha phase, and you see alpha phase is completely gone. Okay, so we changed from alpha phase to beta phase in our fiber and made it piezoelectric. So of course we got a patent on that one. And yeah, so many companies contacted us. They thought, oh, now we can make garments that can generate electricity just by making this. And there was a news article. So I thought it was overblown. But anyway, I'll talk more about that. So we characterized this material, and of course, we published that paper in, again, Smart Materials and Structures. So this is mechanical properties. So in mechanical properties, we don't see that much variation, but the poled fibers are slightly better in terms of if you see here, this saturation is at 20, and this saturation is at 26, right? So the stress at which the yield occurs is higher in poled fibers. That was interesting. I mean, we can't complain if we have higher yield point. So we also had to test its voltage generation ability, which we did by making a structure like this. This is a copper electrode on top, and we align the fibers like this. And this is a transparent electrode. It's called ITO, indium tin oxide electrode, that is transparent. So we used both of them and measured the voltage after dropping certain amount, and it gave good voltage. So that's the characterization. So yeah, once we published that, and my boss, who was the director of Institute of Materials Research Center in Bolton University, he was also an MBA, and he tried to sell the technology to many big companies. So it was a lot of activity at that time. So I was more concerned about doing research, and he was more concerned about selling the technology. That was interesting times. But anyway, he was also, he had amazing ideas. So he used to come up with so interesting ideas. And he wanted me to deposit a photovoltaic cell on these fibers or on the film, PVDF film. Can you imagine depositing a photovoltaic device on a fiber or a film? So after a lot of literature search, I had to go through so many different technologies. There was something called dye-sensitized solar cells. There was something called organic solar cells. There was something called polycrystalline silicon solar cells. And the solar cells that you see is a single crystal silicon solar cell. Okay, so I had no background in photovoltaics, and I had to do the literature search and come up with one type called organic photovoltaic cell. Organic photovoltaic cell was easy because you just coat different organic compounds, and by doing that, you make photosensitive layer, and that generates additional charge carriers when the light hits it. So, and then you deposit electrodes on top of it to extract these electrons, which means extract charge, which means get voltage out of it. Okay, so how do you do it? So how many of you are familiar with organic photovoltaic cells? No, they did not take off. Again, they were similar to, because the single crystal silicon solar cells became so cheap that organic, and they had lower efficiency as well. Organic photovoltaic cells are basically you use some organic um, material that is sensitive to light and generates free electrons basically when light is shined on it. So a, a compound called P3HT and PCBM, when you mix them, you get um, uh, light sensitive material, and you coat that material on top of an electrode first, which is basically a conducting material. You coat that, then you deposit another electrode. So, but if your bottom layer is piezoelectric material, now on piezoelectric material you coat an electrode, then you deposit this light sensitive organic compound, right? And now you, on top of that, you deposit another electrode. So basically what you're making is a piezoelectric material on top of which you're depositing a organic solar cell, which means the top can generate electricity when it's exposed to sunlight, and the bottom piezoelectric film, if you vibrate it, it can generate electricity due to vibrations. So that means if there is wind, the piezoelectric part will generate electricity. But when there is sun, the organic photovoltaic will um, produce electricity. So we made this, for the first time, we made this hybrid device as well. First, we made it on a thin film. That is the process. This is how it looks like. It was a lot of work. First, getting to know what are these compounds. Those were very expensive compounds. And depositing electrodes on PVDF is not easy because when you deposit any metal electrode on a polymer, you damage the polymer, right? So you have to identify a technique that deposits at room temperature, at lower temperatures. And that's what we did here. And this is a hybrid piezoelectric and photovoltaic device that generates electricity from wind or rain, and that top part generates from sunlight. So, and this is, we called it red film or red fiber because the three of us who worked on it, Derman is the PhD student, Elias was my boss. So this is red film or fiber, can generate from elements, sunlight, rain, and wind. Okay, so this is how it looks like. So we did not use the comb structures. Instead, we used dot structures. So the comb structure electrodes are like this, but the dot structures give you more space for sunlight to come in. And this was also red in color. When you coat that color, it becomes red. And so this is the hybrid photovoltaic and piezoelectric device that can generate electricity from. Here, again, we had many ideas on how to improve efficiency because the efficiency of organic solar cells was 5%. The efficiency of single crystal silicon solar cells is about 14% now. There are, again, variations, 14, 16, 12. The efficiency of polycrystalline silicon solar cell is about 10%. And the dye-sensitized solar cell, which is dye-sensitized, is similar to this one, but it's a little more complex in fabrication. So that is about 8%. This is 5%. And we thought of increasing the efficiency by adding carbon nanotubes. Basically, the reason why it was inefficient was when light hits the polymer, an electron is released from these compounds. And if the electron is released, it also creates a hole, right? So the hole and electron should separate out. If they don't separate out, they combine and become neutral again. So we were thinking of ways to separate them out. So that was using carbon nanotubes and so on and so forth. Again, that did not work out either, because by the time you add carbon nanotubes, the liquid becomes so viscous that you can't deposit 100 nanometer. It has to be 100 nanometer film, otherwise light doesn't generate free electrons. And then we made from the fiber, actually, we made a fabric. In the Bolton University had a good textile institute, so we made a fabric. And then the person who came after me, I moved to US after that, and he was able to make a 3D textile to increase the energy density. So the amount of energy you can extract from piezoelectric film. So we characterized the 3D piezoelectric structure as well. And this was also published in a very high impact journal. I think the impact factor right now is 35 or something. So yeah, we had a spin-off company called Fiberlec based on the 2 patents. And the third one was the 3D structure. My 2 first patents, and the third one is my next successor's patent. Based on these 3 patents, the spin-off company started out of Bolton University. Did not last long because I kind of knew we oversold the potential of these materials because the energy density was very low. It was commercially very difficult. And they were saying that we need investment and to improve it, and then we can sell the products. But there were real challenges. So that did not happen. So it was covered by BBC, and we won the UK Energy Innovation Award because we could generate electricity from elements. One device can generate electricity from rain, wind, and sun. So that's just because knowing how materials work. So we exploited photovoltaic materials, another class of functional materials. We exploited piezoelectric materials, which are functional materials. So yeah, I'm 5 minutes early. So well, that's good for question and answers. So in conclusion, piezoelectric materials, as I said, their response is linear. So these piezoelectric, if you apply a current or a voltage on piezoelectric materials, the displacement is very linear. Then this is quite widely exploited in many actuators, including the quartz crystal and sonography as well, right? So these are very versatile materials. They have so many applications. You can think of any application where you need actuation or where you need sensing. I think piezoelectric materials can offer you the solution. Okay, so yeah, there needs to be, again, we did additional work as well. Once I went to US, I tried to combine magnetic and piezoelectric to improve the energy density, but again, did not work. So the problem, we don't see electricity generation from walking or from tents or shirts is because the energy density is very small. Okay? And yes, if you need in special applications where you can't get the power or electricity from any other means, this is a good way. Okay, but if you have other means like photovoltaic solar cells or batteries, then these are not commercially viable. Okay, so with that, I'll conclude and I'll take questions if you have any questions. Yeah, exactly. Come on. I mean, I covered so much. You should have some caution. Yeah. Oh, yeah. Yes. You saw yesterday in hard disk drive, the disk is less than 1 nanometer. I mean, the surface roughness is less than 1 nanometer. That's how smooth it is. Actually, if you look at real mirrors, right, the mirrors that you see, they may not be 1 nanometer, but they're at least 100 nanometers. So, if you take spin coating, are you familiar with spin coating? If you take a spindle and make it rotate at really high speed, put a say for example silicon wafer that has really high uh, or low surface roughness, and put any polymer or any deposition, you can get 100 nanometer surface roughness depending on the speed of the spindle. You can achieve that level of smoothness or roughness. Yeah. Yeah, you can get 1 nanometer in a lot of the nanofabrication techniques you need. And in our work, our PVD, one of the challenge was when we deposited electrode on PVDF surface, we had to spin coat this organic polymer, and the spin coating needed 100 nanometer thickness. So we had to have really good surface roughness, meaning low surface roughness. That was not possible with some of the polymers because the way they are drawn and they're made into film. So we had to really buy good quality polymers that claim low surface roughness. Any other questions? Okay, so my question to you, if imagine, or can you think of any way how you can increase the energy density of this polymer? That's of course $1 million question. Does anybody have any ideas? I told you, right? So the polarization is what causes the voltage, but then getting high voltage is not sufficient. You also need to have high current. So PVDF can give you high voltage, but not high current, whereas PZT can give you both intermediate voltage and high current. So is there any way you can increase the current and voltage? Or is there any place where you think it's commercially viable to use it? Okay, then how many of you are impressed with this kind of material and want to work on it? Yeah. Good. So this is how it starts. I mean, you just get excited by some cool material, and then you jump in, and then you struggle to understand it or get to make a small device or small material. And then you start to have ideas. Oh, I think actually I can make it better. And that's how it started. Actually, when I started in Bolton University, um, they gave me this project. So, and when I started to look at it and started to work on it, then I came up with all this process. And I said, I can continuously make a piezoelectric, because they told me I have to make a piezoelectric fiber and show. And then when I was looking at all other things, there, all other professors, what they were working on, I proposed I can make a continuous fiber in a spindle. So yeah, that was not the part of the objective at all. You say that again? Means, yeah, that's another application where you can. So the other thing is the PVDF material is because it's a polymer, the resonance frequency is low, so it's good for low vibrations. PZT is a rigid material, so if you have high frequency vibrations, PZT is a better energy harvesting material. But if it's low frequency oscillations, PVDF is a better material. Yeah. So normal PVDF versus poled PVDF. Yeah. Okay, normal cloth is cotton, right? Cotton or nylon or polyester. So, whereas that one is PVDF. So the mechanical properties are different, the strength and all that. And PVDF can catch fire probably. So maybe not as comfortable. I don't know the density. So yeah, it is different. I mean, you can't have. But if it generates electricity, will you not wear it? Yeah, that is also possible. Yes, yeah, yeah, true. Yeah. So, or it can be put in only certain area, right? You don't need all over. That's very interesting question. Actually, that's while we were working on that, two companies approached us, one from China, one from US. I was in the UK back then. Both wanted to make fibers that are thermoelectric. And that's completely a different, it's not, thermoelectric materials are not the pyroelectric. The pyroelectricity coming from piezoelectric material or ferroelectric material is very small. So the thermoelectric Peltier cells, that have, it's a Seebeck effect. Okay, so there the materials, you need to have a PN junction in order to get a thermoelectric effect. So that was uh, altogether a new area of work, and we did not even accept the proposal. Yeah, that's a. There are many people working on thermoelectric materials, and making thermoelectric flexible is, there are flexible thermoelectric materials. They also suffered from the same issue. Once you make it flexible, your thermoelectric coefficient, the zeta or Z parameter goes down. Yeah. Okay, so with that, if you have other questions, I'm here. So we'll meet again at 2 o'clock for the next chapter I'm going to cover is just, this is just a recap of bulk processing. I'll just show what are the methods. Probably you have seen them or you have learned them. But then I'll move on to some complicated material processing techniques, how to make nanocrystalline materials and stuff like that. But still at the bulk level. Okay, nanocrystalline long wires, nanocrystalline, um, uh, I wouldn't say films, but ribbons. Yeah. So we'll look at those. Um, and yeah, that is bulk processing. That's not nano. And then tomorrow I'll cover nano fabrication. Okay. And then you can contrast between additive manufacturing. You will see a lot of similarity, lot of differences as well. And you can take ideas from nano fabrication into additive manufacturing and so on and so forth. So you can see different challenges. And when you know a lot of these things, whenever you have a problem, technical issue or challenge, you can always, you will find that light bulb, like you get that idea, oh, I can use this technique to overcome this one. Okay, so that's why you have to learn all these different processes, different materials, um, and additive manufacturing is quite new. So those offer many many solutions to many challenging problems. Okay, so with that, I will conclude. Let's, I think we are breaking for tea now, or yeah.
Now we will now we will break for tea. Tea is followed by demonstration session which will be held in our lab A1011. Uh, please be there on time for the session.